chemistry students, welcome back to physics lesson with me, Pratama. And today we are going to talk about ideal gas. This video, it's about the ideal gas equations, but in more detail, we are going to be covering what an ideal gas is and what the ideal gas equation is, with some practice at using it. So if we are going to be talking about the ideal gas equations, we should probably know what an ideal gas actually is. Well, the good news is that you are pretty much already know UC when we've been talking about the kinetic theory of gas and all of its assumption about how gas behave. The gas that we've been talking about are ideal gas. What I mean by this is that the kinetic theory of gas, it's the way we imagine the individual molecules of an ideal gas to act as opposed to a real one that actually gives you a hint at what an ideal gas is. As its name ideal gas are not really, they are, well, idealized. And that they have many properties that real gas do, but a lot of the stuff that makes real gas very complicated is glossed over and simplified. Ideal gas do not exist. They are just a way of modeling gas that makes it much simpler to do calculations and predict behaviors in order to make things simpler than real gas. Many assumptions are made that are not strictly true, but in most situations are close enough. Luckily, you've already pretty much learned these assumptions from when we talk about the assumptions of the kinetic theory of gases. Just in case they haven't locked themselves into your brain yet, I'll give you a quick recap. Now that the first assumptions we make about ideal gas is they consist of a very large number of molecules that are random motions and obey Newton's law. Basically, this means we assume that our ideal gas contains far too many molecules to even come close to counting, and that they don't act as a group move in any particular direction. Despite each moving around themselves in various directions of various speeds, it's also important that this motion can be explained using Newton's three laws. The next assumptions we make for ideal gas is that the molecules that they are made all have a negligible volume compared to the volume of the container. This essentially just means that the molecules of an ideal gas are many. Anytime smaller than the size of the container they sit in, and lastly, we assume that the molecules experience no forces except when colliding with each other and colliding with the wall's container. When it is collide with the wall's container, the kind of collisions that occurs is inelastic collisions, and we neglect the time. What this means is that we ignore all the little interactions between the molecules like gravity or electromagnetic attractions or repulsions, and say the only time they interact is during essentially instant collisions in which no energy is lost to the environment. Meaning that even if the distributions of energy among the molecules changes, the total energy of the molecule stays the same. Nice! Now that we are all clued up on what an ideal gas is, let's talk about the ideal gas equations. The ideal gas equations can be written in two main ways. PV equals to NKT or PV equals to nRT. The P is pressure, V is volume, and the T is temperature. Now, for the different parts, the capital N in the equations on the left is the number of particles in the gas, whereas the little n in the equations on the right hand side is the number of moles in the gas. The K in the left hand equations is the Boltzmann's constant, which you got a whole video on coming up shortly after this, and the R in the equation on the right is the molar gas constant. Something we'll deal with in the Boltzmann constant. I will give you the video for both of these forms of the ideal gas equations are equally valid. They just deal with two different ways of measuring how much of the gas we actually have. Particle numbers or moles, which you'll remember from our video on moles a while back essentially. Our left-hand equations here is when we are dealing with a true particle number, and the fellow on the right hand is from we are dealing with how many moles there are. The ideal gas equation is very important, so let's make sure we've got it down with the practice questions. Let's calculate how many moles of air are in a meter cube at the top of Mount Everest. Assuming the air is an ideal gas, the temperature up there in summer when people try to climb it is usually about minus 10 degrees Celsius, and the pressure of the atmosphere at that altitude is about 30 kilopascals. So firstly, we need to choose which form the ideal gas equations to use. Let's bring them both back up for a second. Well, we see that the form of the equations on the right has little n in it. The number of moles, just what we are looking for. So we'll use that one. The next thing we need to do is rearrange this guy so that the little n is the subject because that's what we are looking for. All we need to do is divide both sides by RT, and we have it how we want it. N equals PV over RT. Then all we have to do is to get our answer is sub in all of our values. P will be 30,000 because we say the pressure was 30 kilopascal. V will be just 1 as we are looking for the number of moles in 1 meter cube. Then R will be 8.31 because that's just what the molar gas constant is. And lastly, T is going to be 263 because minus 10 degrees Celsius in Kelvin is minus 10 plus 273. That's 263. Plug in that all into the calculator, we find that there is about 13.7 moles of air in 1 meter cube at the top of Everest, and that will do us for the ideal gas equations. For now, as always, we make sure you grasp the key takeaway points. An ideal gas in idealized interpretations of a gas and is one that follows all the same assumptions as the kinetic theory of gas. For example, the kinetic theory of gas describes ideal gas. The ideal gas equations has one form for particle number PV equal to NKT and another for moles PV equal to nRT. Okay, SST students, that is the introductions to the chapter of ideal gas. I do hope you understand about the samples and also the meaning of the ideal gas, what I've explained just now. See you again on the next video. We will talk about this in our Zoom sessions and also WhatsApp sessions. Thank you very much. Bye-bye.